All right, thank you all for coming. My name's Gabe, and I'm going to talk about some of the research I've been doing over the past couple of years. This is funded by ACI CRC Foundation Research, and we've done this at the University of Arkansas new structural lab. So this is stress strain analysis of rapid setting concrete. Okay, so a little bit of background on BCSA. This is a rapid setting rapid strength gain concrete that is used in airfield repair and pavement repair over the last 40 to 50 years. So when we think about CSA when compared with Portland cement, we have about the same amount of strength gain in 1 day as we would typically see with Portland for 7 day, and we have the same amount of strength gain at 7 day with BCSA as we would see with Portland for 28 day. So this is really as a repair material, but there's some other advantages that I'll talk about in a second. And so over the past 40 years, it's been used in various repair methods. This is the Lincoln Tunnel. Back in 2004, they were able to send traffic on that the next morning. Reagan Airport, of course, they're shut down the runway for 3 or 4 hours and able to send planes on it. And just recently, and I believe it was talked about at the last ACI, or a year ago, in San Francisco, they had a talk on this, a bridge hinge reconstruction that they were able to send traffic on the next morning using this. That's kind of how the reconstruction looked. They repair the bars, throw the BCSA in there, or the CSA in there, and put traffic on it the next morning. So what we like about this, high early strength, low setting times, we have carbon emission standards and 30% lower carbon emissions for making the actual cement, lower drying shrinkage, higher sulfate resistance. This is compared with Portland cement. So what are we looking at specifically? Well, something that we wanted to investigate was its flexural behavior. So its behavior in flexural compression specifically. Previously, we made a couple of beams out of this BCSA cement, and we found that overall the flexural performance was pretty much the same as Portland concrete beams. But one interesting thing that we saw, that the deflection at ultimate right there divided by the deflection at yield, which is your ductility index, was a little bit higher for BCSA at early age, right? So this is 2.5 hour beam, right? Or sorry, 2 to 5 hour beam, and then a 24-hour break. And so we saw that it was a little bit higher. This isn't a bad thing necessarily, right? A higher ductility allows us as designers or as inspectors to see that a crack is happening and maybe be able to evacuate a building or something before it actually collapses. So not necessarily a bad thing, we just want to investigate it further. So when we think about designing reinforced concrete beams, this is maybe a little bit elementary, going back to your reinforced concrete beam design. But right, if we have a 2-point loading beam, we have a constant moment in the center here. We have compression. This is a slice through the middle of the beam. We have compression in the top of the beam, tension in the bottom. We ignore all the concrete that's in tension. We have steel that's in tension there, and then we have this linear distribution of stress or strain, and then this kind of unknown distribution of stress, and then we say using Whitney stress block that's an equivalent load, and then using the distance to the neutral axis, we're able to calculate our deflections and our moment capacity. So ways we could have higher ductility, one way is that we could have an increased compressive strain at the top. This is your ultimate strain capacity of your concrete, which ACI defines as 0.003. So you could have an increase in that, which would increase your ability for the concrete in the top to strain and deflect more before it ultimately crushes. The other way is you could have a different magnitude of stress in the top of your concrete, right? So a smaller amount of concrete holds a higher amount of stress. This would move your neutral axis up, move your equivalent load up, and this would increase your ductility. These are the two mechanisms. How we investigated this was, and this is a very common test dating back to the 60s. A few researchers have done that, and I'll show the results from them in a minute, but It's an unreinforced concrete section here, so there's no rebar reinforcement in this. All we're replicating here is the top portion, right? So just the compression concrete of a reinforced concrete beam by applying an axial load through the specimen and an eccentric load. So you can think of this as a bending column, and what we're trying to replicate here through bending it is this linear stress distribution from linear strain distribution from 0 strain to maximum strain of 0.003 theoretical. So by balancing these loads, right, if we increase this load here, we move our neutral axis down and we move our stress linearly up. If we increase this load up here, we move our neutral axis up and increase the slope of this strain distribution. So by balancing those, we're able to keep the neutral axis here the whole time by using strain gauges attached to each side of the specimen. But we also have a virtual strain gauge from the top down on the specimen by looking at the top, right? So we should have linear distribution of strain through here. We paint a speckle pattern. This is for digital image correlation, and we are able to measure the strains during the test and after the test, and we can see that we have a distribution of strains along the section from the top. If we were to map out those virtual strain gauges, we can see that the correlation of strains is linear, which proves in this case that plane sections remain plane. And here's a quick video of the test. So since we have no reinforcing steel and we're just replicating the top portion of the specimen, right, we have complete crushing failure. There's another angle. These are our strain gauges that we have attached, just little foil gauges. So they're quite loud. They shake the whole lab whenever they go off, and I'm very glad we're not testing them anymore because they're kind of scary. I know Dr. Murray is glad that we're not testing them either. So, what are the results of this portion of the testing? Well, for one, we looked at the ultimate strain at failure. So this is the extreme compression fiber of the concrete. This right here is what we would assume for ACI 318, right? We would use these design parameters, right? So beta 1, I'll talk about that in a minute, but alpha 1 is not defined as alpha 1 in 318, but it's defined as 0.85 for the magnitude of compression. And this right here in ACI 318 for Portland is defined as 0.003. So historical data suggests that this value is kind of all over the place, but for the most part, it's over 0.003. You know, sometimes it's a little bit below, but for the most part. I also have Canadian code in here, this dashed dotted line, and then Euro code is this dotted line here. And so our value is in orange there. I'm not sure if you could see that, but it kind of falls in line with historical data. This, to us, suggests that it might not be a reason that we have higher ductility by having a higher strain in the concrete. Might be some other reason. So another thing to look at is the magnitude or the depth of this compression block. Or sorry, not the depth, but the magnitude of this compression block. Here's historical data. ACI defines this number as 0.85, and so it's about within the middle of historical data for that. And we can see our data is slightly higher for BCSA, or BCSA specimens, and one of the reasons, or one of the mechanisms by why we could have a higher ductility is because of this higher magnitude of compression here. This would move our resultant force up, and this would move our neutral axis up as well, which would lead to a higher ductility. So this is one of our conclusions, I guess you could say. Okay, so from this data, we were able to make a stress-strain relationship for the flexural compression specimens, and we did this for 0.36, 0.42, and 0.48 water cement ratios at 7-day and 28 days. So we had 14 specimens that we broke there. 12 BCSA specimens, 2 Portland specimens. One other thing that we looked at was the uniaxial stress-strain relationship of BCSA. So one of the kind of the novel ways that we're going to look into this more is measuring the strains with DIC. We're going to, in the future, we're going to measure the modulus elasticity, ultimate strain, ultimate uniaxial compression strain, and that kind of thing. But we did it a little bit here in this study. So again, we used these digital image correlation cameras. That's what they look like. We had to put a lot of light on these and measure the strains between, we put a virtual extensometer on the specimen and measure the strains. And from this, we can see 3-hour break, 1 day, 3 day, 7 day, 28, and 6 month. And so you can see as the specimen increases in age, it increases in strength, but also in slope of this graph or you could also think of the slope up to 40% of the stress as the modulus elasticity. And here's for the different water cement ratios. And here is our modulus elasticity. This is an R modulus elasticity. This is previous data from another study and how our data kind of falls along that, right, in orange. So we can see that ours is a little bit lower than the previous study with BCSA, but we think this may be due to the type of coarse aggregate that we use in our study because coarse aggregate has a large effect on modulus elasticity. And the uniaxial strain, which isn't measured very often, ACI, I believe, defines this as 0.002 for uniaxial strain, but our data falls pretty nicely within historical data for this. Yeah. And then our conclusions from this, for the most part, we measured the 0.003, fell within historical data, so we're good there. The 0.85, what ACI proposes as your magnitude of stress, 0.85 F prime sub C, ours was actually quite a bit higher than that, which indicates that our compression concrete can actually absorb a lot more stress. And then our beta 1 value, which ACI defines as A, we found was ACI conservatively estimated that value, right? So all these values, I'm saying that ACI and other codes are conservatively estimating this for BCSA. And so thanks to the ACI CRC Foundation for giving us a grant on this research, and CTS RapidSet for sending us the cement for this. So those are my references. I can take any questions.